It's 2:30, so in the interest of time, we'll start because there's going to be another talk here at 4. So we need to disperse and leave the board clean by the end of everything. All right, okay. I'm going to give a shortish lecture on what I've titled the statistical physics of complex ecosystems. And the eco there is in sort of parentheses because, you know, in the end, I have to use some example of some model to tell you about some of these techniques. But I hope that as time goes on during the lecture, I'll try to make clear what parts are specific to the model that we'll talk about today and what parts are potentially generalizable. Okay, and so really there are 3 notes that I want to hit today. The first, which I kind of started off in prehistory in my talk last week, was to sort of reiterate this idea that in many complex systems, which are systems with many, many components, where there are interactions between these components, there's been this long-standing tradition, in particular, sort of propagated by Wigner, of replacing complexity with randomness. Sort of taking a complex system and saying, hey, well, I don't know how to sort of parameterize it, so I'm going to treat it as a random system. We saw sort of a few examples of this during this program so far. And so this is a very powerful approach, and also in ecology in particular, this approach goes back to the work of Robert May in the early 70s. And so really what we're going to do is we're going to take one of these canonical models of complex ecosystems, perhaps maybe the simplest one that you could write down that would be interesting, which is the generalized Lotka-Volterra model. If you don't know anything about it, I'll try and give you a 5-minute crash course on it. And then what we're going to do in the rest of the lecture is try to sort of analyze the dynamics of this sort of model. It's going to be a model where there's going to be many, many species, 1, 2, 3, I, J, all the way to S. And just like I said in my talk last week, we're going to be interested in the situation where the number of species S goes to infinity. Okay, and then of course that's going to mean that we are going to have infinitely many equations to simultaneously solve. And so we're going to come up with sort of clever techniques for how to say something about them. And really our goal is going to be, hopefully by the end of the class, we're going to go from that system with infinitely many equations to effectively one single species sort of model. And we're going to try and write down and sort of derive from this big model the dynamics of this effective single species. Okay, and if you're kind of wondering what is so special about this species, there's nothing special about this species. We're going to work in the limit where all of the species are not identical, they're all different, but they're statistically identical, which is to say that the parameters that we use to sort of talk about how they interact with sort of one another will be the exact same for all species. Okay, so all species will be different, but they'll be statistically the same. And so we're really going to care about one of these species, and then we're going to see how we're going to hopefully say something about the statistics of the ecosystem. Okay, and the way that we're going to do this is essentially something called the cavity method, which is a technique in disordered systems. But also on the way, I'll sort of try and say something about this thing called dynamical mean field theory. And really the key difference about it is going to be whether or not we're going to care about these models or systems reaching a well-defined steady state, or whether or not they're not going to reach a steady state. Okay, so that's our kind of goal. Obviously, I'm not going to be able to cover everything about this sort of material here. And so if you get interested in this stuff later, and if you want to take a look at sort of references, there aren't textbooks, but there are 2 references that I'm leaving here that I think are a very good set of lecture notes. Perhaps I would say like the best material is out there at the moment, but by no means perfect, that you can use to sort of read more about, especially in the ecosystem context. Yeah? Okay, and yeah, feel free to stop me at any point if something is not clear. At some point, if I notice that I'm going way over time, then I'm going to try to stop questions, but then just come to me after the lecture is over. Okay, like I was saying, we're going to care about systems with many, many particles, or in this case, many, many species sort of interacting with each other. And so for this lecture, the model that we're going to care about is the generalized Lotka-Volterra model, or if you go into the rabbit hole of the ecology literature, you'll often hear GLV all the time, and so that's the model that we'll deal with. And very roughly, sort of, most models in ecology will look something of this type. So what I'm doing here is there's n sub I, which is the abundance of species I. So really what we are doing is that we're imagining that we went to an ecosystem. There are many, many species there. And we want to look at how, what are the sort of different population sizes of each of these species. For what I'm going to talk about in the rest of this sort of lecture, don't worry about the population size being a discrete number. We're just sort of taking these population sizes, normalizing by them by some sort of carrying capacity. So in the end, these n sub i's are going to be some continuous number, right? And so the n sub I means the abundance of species I, n sub j means the abundance of species j. And what we care about when we're tracking the dynamics of the sort of system is to know how these n sub i's all change, right? So we care about this n vector as a function of time. And almost all ecological models, in some sense, are going to be of this form, where this ni dot, which is the rate of change of the abundance of species I, is ni times some function g of I. Okay, and this sort of idea of this n of I being an explicit thing that I take outside, it's sort of very, very common. And at the first time you sort of see it or hear it, you can be like, okay, why do I have to worry about this thing separately? Why can't I just throw this in? The idea here is that this is really the acknowledgement of the fact that, ni equals 0 is something special. So can someone say, I mean, just so that we feel a bit oriented, can someone quickly tell me what ni equals 0 would mean? Yeah. It's not everyone's dead, but species are, just there are no sort of individuals of species I present, right? So the idea is if there are no individuals of species I has gone extinct. And so no matter what's going on the other side, this ni dot stays 0, right? So this is kind of a special thing that other models that you may write down of other things may not apply, but sort of ni equals 0 is sort of a special thing in ecology. And so in some sense, whatever remains on the other side of this g sub I, is just can be whatever function that you might imagine. But in some sense, the interpretation of this is that this is the per capita growth rate of this species, right? And what do I mean by per capita growth rate? I mean the total growth rate normalized by the population. Right? Just like on average, is an individual growing or dying, staying the same, right? And so in some sense, in almost all of these ecological models, we're writing down what this per capita growth rate might sort of look like. It might look like an arbitrary function. And the sort of special thing about the Lotka-Volterra model, like many of you might have heard that it's the simplest model of ecology. The way in which it might be the simplest model is that it's just a case where this g of I function is linear. Okay, and what do I mean by the fact that it's linear? It means that basically, if this g of I depended only on ni, what would that imply? Would that suggest that there are any ecological interactions at all? No, right? I mean, then just the growth rate of species I only depends on I. So the fact that this g of I depends on this entire n vector is, in principle, is sort of signifying the fact that the growth of species I may depend on j, k, and so on and so forth, right? And so really what you're doing in the Lotka-Volterra model is writing this g of I as a generic linear function in all of the species abundances. There are many ways of sort of writing this model down. This is the way that I've chosen. Okay, so this, all I've done is I've written down this g of I as some sort of linear function of all of the species abundances. And so the key idea is that there's a k of I sort of sitting here. This, maybe to get sort of an intuition for this k of I, let's just sort of imagine the case where we had only one species. Okay, so there's one and only one species. I don't really have to worry about all of these terms over here. what do you think would happen to these, to the dynamics of species I if I started off at a small abundance? It'll grow, and will it ever stop growing? Yeah, when it reaches something, right? And I heard someone say carrying capacity. So what is the carrying capacity of the species I? Ki, right? So in some sense, the easiest way to think about this K of I is that this is a carrying capacity of the species I, right? And so indeed, if there were no other interactions with other species, this is the sort of stuff hiding here, the species would grow exponentially at first, settle at some carrying capacity K of I, the dynamics would then stop and stay there forever. Right? So the main thing that's happening with the presence of other species is captured in all of these terms over here, right? And so in particular, what this is saying is that the presence of species J will change the growth rate of species I by a coefficient that we call Aij. And this Aij is very appropriately called the interaction matrix. Right? This is kind of a matrix that's encoding how much species J influences the growth of species I. Right? So that's the convention that we're going to use here. Ij means J influencing I. Ji is going to mean I influencing J. Right? So all of the interactions are over here. Right? And you could have imagined a more complex model in which this G of I was not just linear. There could be other terms that were Nj and K, Nj and K and L, and so on and so forth. That's not what we have here. Okay, so is the sort of what the model dynamics are clear? I haven't told you anything about where these Ki's come from or where these Aij's come from. Okay, and that's exactly what we're going to talk about now. Yeah, so like I said, this is a system where I've written down one equation for one species, but we should always remember whenever we're sort of solving any of this, that in principle, every species has one of these equations, right? So what we have is that this is essentially encapsulating S many equations. And remember, we are interested in the limit where S goes to infinity. And so what we need to then ask ourselves is where are we going to get these Ki's from? And where are we going to get these Aij's from? Right? And that's sort of where the idea of complex to random comes in. Right? So the very pithy idea is that Ki's, the carrying capacities of all the different species, are some random variables that come from some sort of distribution, and we have to define that distribution. And these Aij's, which are the interactions, also come from some distribution, right? Which is that how J influences I, this thing over here is my Aij. I have to specify an Aij for all of the things in this sort of network, and that also is going to come from some distribution. And the idea is going to be whatever choice of distribution I make is going to influence the results that I get in the end. Okay, so what I'm going to do next is I'm going to tell you the ensemble that we're going to use for today's lecture, and we're going to stick to this. And I warn you in advance, whenever I write down this ensemble, usually people have questions about why it's written this way and whether or not biology is like this or not. Don't worry about that for now. Of course, whatever I write down is going to be a case, and I by no means will say that it's realistic. It's just going to be something concrete that we can write down that will help us solve this sort of problem. But before I do that, let's just be clear about what our goal is at the end of sort of doing all of this. Yes? By the intrinsic growth rate, you mean something that I have hidden over here, which is this thing sitting here? Yeah, so in principle, I mean, yeah, like I said, there are different ways in which people write down this sort of model. There are some who would write down a specific Ri here and write down a Ki somewhere else, maybe sort of somewhere here. You could do that. So in this particular instantiation of the model that I've considered, the intrinsic growth rates are all, this K of I in some sense is both the intrinsic growth rate at low sort of population size as well as the carrying capacity, right? So you can imagine when Ni is very, very tiny, there's no other species, Ki is exactly the exponential growth rate at which this species I is growing. But it also happens to be the long-term carrying capacity. Is that clear? Of course. So this is where we get into, oh, but biology is like this or like that. Of course, they could be, yeah, you could, of course, make them two different parameters, and that would be fine. In what I'm choosing to write down, there's only one just for simplicity. Yeah, there's another version I could write down where all the KIs would be one. Okay, good. Yeah, so usually in this kind of exercise, our goal would be sort of maybe a few different things. One of the things that you might want to know is, once I give you all of these parameters, Ki and these Aijs, you want to say something about what the dynamics of the system will proceed to, right? So you might want to say, hey, these are all my Aijs, these are all my Kis. I'm going to run the dynamics with some given initial conditions. What's going to happen at the end? Am I going to reach a steady state? That's one question. If I reach a steady state, what are the abundances of the different species going to look like? Are all the species going to survive by the end of it? Are some of them going to go extinct? If some of them are going to go extinct, what fraction of them is going to go extinct versus survive? These are all questions that you might have naturally, right? And so many of these questions we're going to be able to address once we arrive at this effective single species equation, which we're sort of headed towards. Okay? I don't know if it's possible to turn on the air conditioning, and maybe I'm the only one who's sweating a little bit standing here, but if there's someone listening and can turn on the air conditioning, that would be very useful. I am wearing a jacket, which was totally fine in the morning when I wasn't giving a talk. Okay, so let me say something about how it is that we're going to draw these KIs and AIJs. And we're really going to do the simplest thing. We're really going to imagine that these KIs come from some Gaussian distribution. And these AIJs also come from some Gaussian distribution. So let me just say quickly what it is that we're going to imagine for these KIs. I'm just going to say that all of the KIs are some K plus some sigma K times Zi. Okay, which is to say that all of my species carrying capacity are going to come from some Gaussian distribution with a mean K, standard deviation sigma K, and the Z of I is some standard normal variable with mean 0, variance 1. Okay? Fine, you might again say what gives me the right to choose this parameterization? Nothing does. It's just a choice that we're making. Okay, so this one's simple. The next one is also simple, slightly less simple, which is what do we do about these AIJs? Okay, so the simple part of the AIJs is the following. So they again have some mean, which I'm going to call mu over S. There's a simple part here and a non-simple part here. And plus some little fluctuation, okay, which I'm going to write as sigma times little Aij. Okay, so just to sort of remind you, this S is the number of species. Which eventually we're going to send to infinity. Right? This mu is a parameter, right? So really what this is saying is that all of my capital Aijs, which are, so Aij is again how species J affects the growth of species I, they're all going to have some mean, mu over S, and some sort of variance. So the sigma is again the sort of standard deviation. The only twist to this little Aij is that it's not yet another standard normal variable. You have to define some sort of statistics for this little Aij. And the statistics that I'm going to define are going to be the following. The mean of all the Aijs is going to be 0, right? And that's indeed something I need if I want my capital Aijs to have a mean mu over S. Yeah. And this And the fluctuations in Aij, I'm going to write in the following way. Okay, can people read stuff that I've written over here? I hope you can. I mean, I'll read it out as well. So this first thing over here says that the mean of these little ij's is 0. Second thing over here talks about the fluctuations. And really, there are two sort of parts of it. Let's talk about the simple part first, which is just the variance of all these of these little aij's is sort of 1 over s. Okay. And at this point, you might be asking, what are all of these 1 over s's doing here? What is this 1 over s doing over here? What is this s doing over here? Does someone someone who doesn't know, care to say something about why you think the s's are appearing in this way that I've parameterized things? Yeah. Okay, good. So you're saying that I want something to sum over to 1 when yeah, can you say a little bit more? By this, you mean this, right? Okay. Yeah. Why should the variance end up as 1? The mean is mu over s, right? Okay, I think I'm getting what you're saying. Maybe I'll try to say it in my own words. So let's imagine a case where I did the same thing that I was kind of doing here. My aij's were all some mean mu plus some sort of fluctuations. Yeah, and let's say this mu was a finite number, right? You're right that something funny would happen here. Can people see what's the funny thing that would happen here? What would the mean, yeah, what would this term on average look like? Remember, this is a sum over s many things, right? So this is like mu times n plus mu times n plus mu times n plus mu times n s times, right? What happens when s goes to infinity? It blows up, right? And so if your per capita growth rate blows up, you have a problem. You don't have a well-defined model, right? And so in some sense, you can imagine, okay, if I want my mu times n added s times to be something that doesn't blow up, stay sort of finite, the simplest thing that I can do in life is to essentially scale down all of my per species interactions by a 1 over s factor. Yeah. Could I do it as a 1 over s square factor? Yeah, because then I'd have 1 over s, right? So in some sense, this 1 over s choice is something that's called having a well-defined thermodynamic limit. And so we want this model to have a well-defined thermodynamic limit. And so that's what this mean of aij must do. And if the mean of aij must scale with s, the variance of aij must also scale with s. Yeah? Okay, so usually this thing sort of trips up, folks. So hopefully this is somewhat clear in the time that I can make it clear. The variance also has to do this. The only sort of other funny part about this parameterization is this rho delta IL delta JK over S over here. And really what this means is that the choice of the ensemble that we're making is the following. So I have my Aij matrix. So remember, Aij means how J affects I. This matrix has a diagonal, which are all like my AIIs, which is about how species are influencing each other, which the way that I've written out my model are all ones. And so what this rho thing over here is saying is that I really need to care about diagonally opposite elements. I want to care about Aij and AJI. And what this sort of parameterization over here says is that they're not uncorrelated, but instead they have a correlation rho with each other. This rho is a parameter that we can choose. So when rho equals 0, all of these elements of this matrix become uncorrelated with each other. If rho equals 1, then we have the fact that our interaction matrix is symmetric. The way that I affects J is the same as how J affects I. And if it's negative, then it's an anti-symmetric matrix. You can imagine like a predator-prey interaction, for instance. Okay, so this rho is really kind of controlling what we think of the interactions in this ecosystem to roughly look like. Okay, and so that's really it. Remember, we needed to specify something about our KIs and our AIJs, and we've sort of done so now. And let's just keep track of how many parameters we ended up with. So we started off, of course, with S squared parameters here and S parameters here. We now don't have S squared plus S parameters. Let's just count them. We have 1, 2, 3, 4, and 5 parameters, right? So to go from infinity to 5 is pretty good. And so in the rest of sort of what we'll care about is I give you these 5 sort of numbers, and you tell me as S goes to infinity what the behavior of this system of many, many species is going to be. Okay, so is the problem clear? And the goal is clear? Okay, so now in the time that we have left, let's just begin to think about how it is that we're going to solve this problem. So what we really have to solve is we have to solve many, many coupled ODEs of this type, right? So the way that we're going to do this is we're going to use something called the cavity method. And while I'm talking about using the cavity method, I'll say sort of one more simplification that we'll make for sort of ease of calculation and time, which is that I'm also going to assume that the long-term behavior of the system that we're interested in is the behavior where the system goes to a well-defined steady state. Okay? I'm going to assume that this system reaches steady state. And what that means is that I'm only going to be interested in solutions where this LHS, where everyone goes to 0. Okay, I'm only interested in solutions with that type. Okay, and so, I mean, this sort of cavity method has sort of many steps, and once you start doing the algebra, it's easy to get lost. So what I try to do is in the next 5 or so minutes, sort of sketch out something and tell you generally what the intuition of the method is, and then we'll see how far we go into actually implementing the steps of the method. Before we do this, are there any questions about the setup? And I know I took 25 minutes to set it up, but I think that's fine. What do the solutions mean in this case? Yeah, so the solutions might, okay, good. That's actually a great question. What will the solutions look like eventually, right? So remember, at the end of this, whatever happens to the system, what we're going to have is a bunch of species that have gone extinct. That is, the way that they satisfy this equation is that Ni for them is 0, and a bunch of species that haven't gone extinct, right? So the 0th order question that you might ask yourself is what fraction of species has gone extinct versus what fraction of species has not gone extinct. This is a number that people will often call, and those references will definitely call phi sub n. It's a number between 0 and 1. 0 means all species went extinct. 1 means no species went extinct. And really, all of the other things that you might care about are what happens to the surviving species, which is that in particular, all of the surviving species are going to have some abundance at steady state. And so you might want to know what all those abundances look like. And so in particular, of course, you won't be able to predict what any species' abundance is. All you'll be able to do is to say something about the distribution of the abundances and Ni. Okay? And indeed, what we're going to find is that that distribution looks like a truncated Gaussian. The reason it's truncated is because of all of these extinct species sitting here. So there's a whole bunch of species that have 0 abundance because they're extinct. And then there's a whole bunch of species that have non-zero abundance because they've not gone extinct. And because this is a truncated Gaussian, all you're going to need to care about then is just the first 2 moments of this distribution. Okay, so really we're going to try and solve for these 3 numbers. What's the fraction of species that survive? What's the mean abundance of the survivors? what's the variance in the abundance of the survivors. We're not going to get to the solutions in this class for sure, but you're going to see what is the equation that you're going to need to solve to get that answer. Yeah. Yeah, okay. Good. Yeah, so you're one step ahead of me. So the question is, it seems kind of surprising that the distribution is normal as opposed to something more skewed like a log normal distribution. And indeed, this has to do with what you're assuming about the KIs. So because we've assumed that these KIs are sort of normally distributed, this is what we get. You might assume something else about the KIs and you'll get a different answer. Yeah. So in the end, some things are going to depend on the ensemble. Some things are not going to depend on the ensemble. Yeah. Yeah. Why does the Gaussian truncate at 0? I think it's just really because what is going to happen, the intuition is that really this G of I, which is the growth rate, because all the things that go into it are random variables, this growth rate becomes a random variable, right? And the idea is that this growth rate has consequences for whether you survive or not. So if this growth rate becomes negative, you're going to die. This growth rate becomes positive, well, I mean, this growth rate eventually will become 0, you're going to survive, right? So that's really, so there's something special about what's happening. And that's all because of the nonlinearity that sits outside. If this were indeed a linear model, which by the way, reference B over there, we'll talk about how to do this entire procedure with linear models. Then you'll see that you won't have this funny picture. Like I said, some aspects of it are ensemble dependent. For instance, what the distribution of KIs is going to change, whether it's a truncated Gaussian or not. Some things are independent. Like if this were a uniform distribution with the same mean and variance, then you would still get a truncated Gaussian. Okay, so yeah, let me try and say something about how it is that you actually go about saying something about these equations. So the idea of the cavity method is the sort of following. You start off with a system of size S, okay? So I'll sort of draw again these nodes and arrows that I was drawing sort of here. Are people sort of clear about what these kind of diagrams mean? Each of the nodes here are different species. Each of the arrows here are a feeble attempt to represent the interactions between them. And so really, node 1 is species 1, node 2 is species 2, and so on and so forth. So you sort of start off with a system with S species. And what you're going to do, and so you assume something about what's happening to this system with S species. So what we're going to assume is that these S species are at a steady state. That's just for ease of calculation. Again, I mean, if I get to the generalization, you don't have to assume this. And then what you're going to do, and that's why the sort of name of this method is cavity method, is that you're going to add another species to this system. Okay? And that species I'm going to label with a little 0 over here. Maybe I'll do it in white. Just to sort of remind ourselves that all these species have numbers 1, 2, 3, 4, 5, and so on and so forth, all the way to S. And you're adding one more species to it, right? So you're making the system size go from S to S plus 1. And this species is appropriately called the cavity species. And so really what's happening in the method is that you're going to, that you're trying to ask, I add a species to this system. This species will now affect all of these other species that were already present in the system, right? So you have, maybe I'll draw in pink here, the way that this cavity species interacts with all of the others. And because this species generically interacts with all of the others, it will of course change the abundances of all the others, right? So sort of step 1 is that you start off with these S species. Step 2 is that you add this cavity species. Step 3 is that you ask for how are the S species affected by the cavity species? By 0. You try to say something about that. And then can you guess what you do the next time? Is it only the fact that the cavity species is going to affect everyone else? All of the others are going to affect the cavity species back, right? And so indeed, in the last step, what you're trying to do is that how is 0 affected by all the others? And somehow by following all of these steps, by the end of it, you would have written an equation for what happens to this species 0. Okay? And that equation is going to be our effective single species equation. And my claim is that whatever I learn about species 0 is going to be generalizable to any other species in the system, because the way that I'm going to add this species 0, it's going to be statistically identical to all of the other species, which is to say it's going to have a ki that comes from the exact same distribution as for all other species, and it's going to have aij's, meaning ai0 for how this 0 affects all the others, and a0i for how it's affected by all of the others. They're all going to come from that same ensemble. There was a question. Yeah. Perfect. Exactly. So what you're going to do is, by the time you get to step 4, you're going to get an equation for the 0th species dynamics, and you're going to then ask for the steady state of that. Okay? So, and then the claim is that that will give you the steady state of this system of S+1 species. Okay, so then in step 5, if you care about steady state, you probe for the steady state of N0 dot. Okay, is a general idea clear? In basically every instantiation of the cavity method, this is exactly what you're doing. Okay? So I'll leave this cartoon over here, and I'll go back to this side of the board, and then we'll do all of these steps out for this sort of model, and then we'll see whether or not we actually did all of those steps. Okay? Yeah. Good. Yeah. Exactly. Yeah. Thanks. Thanks. Was there more to your question? Good. Okay. Okay. So you're really going many steps in the future. So yeah, yes. So I mean, the reason that this model is very nice is that it's very easy to sort of do all of these steps out, because G of I is linear. You just solve linear equations. If it were non-linear, you then have to do something. One thing that you can do is, well, you can linearize that system and assume that you were at some steady state, and the new steady state that you went to is not too far from that. You do what you do to survive. But yes, indeed, the main point that I want to sort of reiterate is that really those steps that are pointed out there, you may imagine that there are no species there, there are just particles. And then essentially that's kind of what you're doing for other systems as well. Right? So here we didn't really write anything about G of I or K of I and so on and so forth. So really this is a general prescription of what you're kind of following. Yeah. And indeed, you follow the same prescription where if you were not in steady state, you would care about trajectories, and then you'd ask about how this cavity species perturbs the trajectories of everyone. Okay, if that feels very abstract, that's fine. Don't sort of worry about it. Yes. Yeah. Good. Good. Mm-hmm. Yeah, so the question is that since S is large, yeah, how do I think about cavity species affecting everyone else? This is indeed the first step that I'm going to do out, but I'll tell you the answer sort of straight away. The idea for why you want, at step 1, you want S to be large is exactly the fact that this cavity species is going to roughly exert a 1 over S effect on everyone, right? And since S is large, this 1 over S effect is small. And so essentially, when you do step 3, you're going to be able to invoke linear response. And that's what's going to make some things quite easy. You don't neglect it. Yeah. Exactly. So you neglect. All of this will become clear if you give me 2 minutes and you see this in action. But yes, you will neglect second order things. Yeah, because I'm sensing that some of the students, it's not obvious to them what are second order things and what are first order things. So then, it's really for the students. Okay. Okay, I hope everyone has a model written down somewhere, because I just erased it. Okay, so let's kind of do this stuff in action. So the first thing that we're going to do is that we have a system without the cavity species that's at steady state, right? So what I have and the sort of terminology I'm going to use is I'm going to care about the abundance of species I without species 0, right? This is the system without the cavity species. I have this system at steady state. So ni without 0 dot equals 0. And so all that means is that ni without 0, ki minus ni without 0. Okay, so all I've done is I've written down the condition for step 1 to be true. This is the system where I don't have the cavity species, which is present at steady state. And so what that means is that for all I, this has to be true. Okay? So I have some ni without 0. This is the abundance of species I before I introduce the cavity species. The abundance of all other species j before I introduce the cavity species aij, of course, is not going to change when I introduce a new species. This is an assumption of this model. Ki also doesn't change, right? Okay, so now the question is, what's going to happen once I introduce this cavity species? Okay, so can someone say something about what will happen to maybe this equation 1 once I introduce this cavity species with abundance n0? There will be a new term that goes into the end, right? And do I still write down these ni without zeros? No, right? I mean, now I have this species 0, right? So in principle, if this new system reaches steady state, then I must have that ni now not sort of without 0. If I say ni, now that's sort of with the cavity species included, follows something like this. Okay, so I've done 2 things here. One is all of the abundances went from ni without 0 to ni, nj without 0 to nj. I don't yet know what those are. And I had another term that comes from the fact that I included a cavity species. And so this ai0 is precisely how cavity species 0 is influencing the growth rate of species I, right? And again, there are many, many equations of this type. I haven't written all of them down. There's also going to be an equation for the dynamics of this cavity species n0. It's a new equation that I've added to the system. I'm not going to write it now. You don't have to worry about it for now. We'll worry about it at step 4. Clear? Yeah. Clear? No. Why? Because basically what I'm doing is these are 2 different steady states. Okay, this is a steady state of all the species without the cavity species present. So my set of abundances, if I think of my abundance vector, that's n without 0. This is a new abundance vector because this is a new steady state with the cavity species added where there is no without 0. Yeah, good question and good sort of clarification, right? So all of these NIs and NJs are the new abundances of all the species after I've added the cavity species. Okay. And again, I mean, you might say, well, you don't know what the abundance of the cavity species is. I don't. I'm just writing the equations that must be true at steady state. Good. Okay, so now we can ask ourselves, what is it that really happened by me adding this cavity species? And can someone say really what is it that happened to the dynamics of any species I? Someone said this before, right? I added a new term. That's this guy over here. So sort of I noticed something interesting. I could have written this term down not here. Could have kind of written it down next to this term. Not the prettiest way of sort of writing this down, but I'll sort of put it in a cloud to make it clear sort of why I'm doing this, right? So if you look at this thing over here, all you'll say is, well, these equations look the exact same. This one has a carrying capacity Ki. This one has a carrying capacity Ki minus this blob over here, right? They're just the same dynamics with slightly different carrying capacities, right? So in effect, what you can think about is that the addition of this cavity species just changed the carrying capacity of every species by some amount, right? And all we need to ask is this amount large or is this amount small, right? And so that's something that we can do now. We can see very clearly that this amount should be small. Why? Because this term, AI0, well, any of these AI0s are roughly 1 over S, right? Well, N0, I don't know, but roughly they'll be, let's say, order 1-ish. They're the abundance of these species. This Ki are carrying capacities, which are also going to be order 1. And so this is kind of like an order 1 over S correction to the carrying capacity, right? So it's a small, so when S is large, this change to the carrying capacity is small. Okay, if that's confusing a little bit, come to me after the class, because I really want to run through a few of these steps just so that you see this entire picture. If this is not clear, some of the other steps about what is small and large might not be clear, so don't sort of worry about that. Once you get into the habit of thinking about small and large, then they're all sort of trivial and simple. But all I want to assert for now is that the addition of this sort of cavity species makes a small perturbation to the carrying capacity of all the other species. And so once I do that, the thing that I'm going to impose is I really want to write down the abundance of species I after introducing the cavity species in terms of the abundance of species I without the cavity species, which is to say what the abundance is post the perturbation versus what the abundance was before the perturbation. And my assertion is because this sort of perturbation is small, I can sort of write it down in the following way. Okay, if that seems funny, let me unpack this for you. And actually, let me write this down in a more general way. Okay. So what I've done here is I've said, look, the abundance of species I post the perturbation is going to be different from the abundance before the perturbation by this amount over here, right? If you just think about it, all I've done is I need to know if I make a small change to the carrying capacity of species J, how much does it affect the abundance of species I? And just need to multiply that by how much I change the carrying capacity of species J by, right? And I just add over all of the other things. Remember, this was just showing us that the carrying capacity of species I changes, but in the same way, the carrying capacity of species J changes, K changes, L changes, and so on and so forth, right? So in effect, every species is going to be affected by the change in the carrying capacities of all the other species, right? And so this sum is doing that. Yeah. This delta Jk, this delta Kj is exactly what we've written down over here, right? It's how much the carrying capacity of species J changes by, and that's minus AJ0 N0, right? I told you what it is for species I, for species J, it's the same thing, just with a J, right? The thing that you might find funny here is this sort of matrix sitting here, right? It's some matrix, right? And in fact, we're going to call this nu ij. And it has a specific name. It's a susceptibility matrix, right? And it's called a susceptibility matrix for a very obvious reason. It tells you how susceptible the system is to small perturbations in sort of parameters. You might say, hey, Akshit, I don't know what this susceptibility matrix is, so why are you writing it down? It's true, I don't sort of know it. What we're going to do is we're going to assume that this is something that we don't know. And so we're going to introduce it as a new unknown in the sort of problem. And then in the end, our aim is going to be to solve for everything, including this guy. Okay? That might seem funny, but it's going to prove very, very useful. And actually, in general, if you sort of go into sort of reading more about this stuff, what you'll find out is that these susceptibility matrices really encode a lot of cool stuff about what the system does, not just for ecology, but in any sort of multi-component system in general. Okay, so is this idea clear? Yeah. So now what I can do is I can write down the abundances of all the species after adding the cavity species in some sense, in terms of what they were before. Okay. Okay. So now I have just enough time to do the last step before we get to the final equation, and then I'll leave you there. Yes. The last line here. Yeah. Yes. 1 minus rho coefficient. No, it's not. There's a sigma sitting here. No, it doesn't because of this, because of the way I've written these deltas over here. If you're confused about that, just come to me after the class. Okay, good. We're all good. Okay, so let me just try to write down this final step over here. So what I've done is, so I've done this step. I've taken the system with S species. I've added the cavity species. I've asked how the S species are affected by the species 0, right? How are they affected? Well, I didn't write here 3, right? This tells me how all the species are affected by adding the cavity species 0, right? So it's an equation that tells me how all the species are affected by species 0. And all I need to do now is step 4. And you'll see why I wrote this step 3, which is how is it then finally the cavity species is affected. So what I'm going to write down here is, in principle, an equation I should have written down alongside with step 2, which is what's the steady state for the cavity species, right? And just by now it's sort of boring, but I write it down the same way. Right? So if this cavity species is at steady state, it'll have some abundance N0. And then this Nj are all the abundances of all of the species after adding this cavity species, right? And so now you can see this exact thing over here is something that I need to plug in from somewhere, right? And that's exactly step 3. Okay, so what you can do is you plug in step 3 into that circle over here in step 4. And you end up with the following equation. Kind of skipping over the algebra, but trust you can do it. Okay, so what I've written down here is just substituted step 3 into this thing over here. And I've ended up with basically something in terms of N0, this new JK, and all of the abundances of all the species before, right? Which I don't know yet. Okay? And if I were to solve it, that's going to be the solution. I'm going to talk about why it's a solution. So in case you're confused, hold on for a second. Okay, so what have we done in these last two steps that seem a bit cryptic? Well, algebraically, we've just substituted in all of the things that we have over here. What we've ended up with, can I take maybe 2 or 3 more minutes? Okay, just to sort of finish off the thread that I started. Okay, so what I've sort of ended up with here is an equation for the abundance of this species 0, this cavity species that I sort of started with. And then I very boldly sort of written down something that looks like the solution to this equation over here, right? So if this seems a bit funny, all I've done here is just the following. This is this nonlinear equation in n0, right? There's an n0 squared over here. We already discussed at the beginning of this class that it's either that n0 is going to be 0 if this thing reaches a steady state, or it's going to be non-zero, in which case this whole term in the parentheses is going to be 0. Right? That's the only way for this entire thing to be at steady state, right? So really all I could have as a solution to n0 is either that my n0 could be 0, or my g could be 0. And if n0 is 0, then of course, my abundance is 0, and my per capita growth rate would be negative. If it's non-zero, then I don't have to worry about this n0 over here. Then this is just a linear equation in n0, which you can solve, and that's the solution. Okay. Still not over yet, but all I want to sort of just give you a sense of is the following. It might seem by looking at this equation that you need to know all of the abundances of all the species before I added the cavity species, right? It turns out I don't. Okay. The reason for that is the way that these abundances enter this equation is through a sum. Okay. And what's really happening here is that this sum has 2 parts. One is how species J affects the cavity species, and the other is the abundances of all the species before I added the cavity species, right? In principle, those 2 things have no relation to each other. Of course, the system before I added the cavity species knows nothing about the interaction that the cavity species is going to have with the species, or sort of vice versa. So what I end up with is essentially a sum of many, many weakly correlated variables, right? And does someone know what that is? That's just a Gaussian, right? So I just invoke the central limit theorem on this sum, and this is going to give me a Gaussian with a mean k0 minus whatever the mean of this is, divided by something over here, which you can also show that in the sort of large n limit converges to some number. Okay. And then in the end, this is sort of the origin of this truncated Gaussian that sort of we were talking about, right? So there's 2 parts of this truncated Gaussian. One is the truncation, which you can see pretty clearly. The other is the Gaussianity, which comes essentially from the sum of sort of many, many weakly correlated things. And so here also now you can see if I had different ensembles, how this would change the answer, and so on and so forth. Okay, so I'll kind of end here. There are many things that I haven't sort of told you, and so it might seem sort of incomplete. For instance, how do I say what fraction of species go extinct, and so on and so forth. All of them are going to be encapsulated in somehow solving this equation in the box along with a bunch of other things. Okay, and so if we had more time, if you were taking a whole course, this is exactly what you would learn over the course of a few different lectures. But I hope this sort of gives you a sense of how you go about sort of analyzing systems of this kind, right? And how sort of these 4 steps were incorporated, right? When you're doing dynamical mean field theory, you're doing essentially the same set of steps, except you don't invoke steady state. You just think about trajectories. Okay, all right, so I'll end with that. It's the end of the class. So for those of you who want to go, feel free. For those of you who have questions, you can either come to me here, or you can say your questions from over where you are. Yeah. Yeah, you're indeed right that it's not immediately clear in any way how you go about computing the susceptibility matrix. I can't give you a pithy answer to that, except that this is one equation of a few that you write down. I mean, really, there are four unknowns in this problem, right? Three that I pointed out to you before. One is the fraction of surviving species. One is the mean abundance of surviving species. One is the variance in the abundance of the surviving species. And the final one has something to do with the susceptibility. I mean, in principle, it doesn't sound like one unknown. It sounds like an S by S matrix, right? It turns out that actually the only way the susceptibility shows up is through this sum. I mean, that you can see. And so when you actually analyze what this sum looks like when there are a large number of these particles and you put in this ensemble, you'll see that the only thing that matters is the trace of this matrix. And so it's really one number that really you don't know, which is the trace of this matrix. So you have four unknowns, and somehow from this you squeeze out four equations in those four unknowns, and then you can solve them. Okay, and again, I haven't told you how to do that, but I don't know how to do that in the next 1 minute. Yeah. Yeah. You absolutely could have told that, because remember, the correlation is only coming in when you're sort of considering diagonally opposite elements. This is a very different kind of correlation, right? This, what I said, is always true, right? There are two different things that don't know about each other at all. System before the perturbation doesn't know anything about what's going to happen in the future, which is it doesn't know which cavity species you're going to add, right? So this is always going to be true no matter how high or how low rho is, that A0j is not going to be related at all to nj without zero. And these are the two things that are uncorrelated. Yeah, the abundance of species without the perturbation and whatever it is that the cavity species interacts with. Yeah, that's going to depend on rho. But you'll find that in the end that sum depends on rho, but it's not like you can't solve it for any particular kind of. Yeah. Exactly.
Other cases, not perhaps not here, but elsewhere, where you have multiple ansatz that still solve the same equation.
That's a good point. The question is, are there cases where there are multiple ansatzes for what you assume about nj without zero, and then you can still solve it? I can't think of any off the top of my head, but yeah. Yeah, it's all about self-consistency. Yeah. Yeah. Okay, question is about if you perturb the equations by adding some sort of immigration, does it go all over the place? No, not really. And in fact, what I was, I mean, this is not the exact thing that I did in my talk last week. In my talk last week, I also had stochasticity and I had all these other things. So this general framework can incorporate all of that. Yes, you had a question, right? Okay. Yeah, I mean, so generally, I mean, I can't give you a general answer for when it'll work and when it won't, but this is the prescription that you could try and use to sort. I mean, now whatever questions you have in life, go with pen and paper and try to work it out, and then you should be able to tell me the answer. Yeah.
One of the existing species.
Yeah.
Then these two things will be correlated.
Yeah. So the question is in my talk last week, the way that I was adding a new thing was that it was very correlated with one of the species that was already present in the system. It was a mutant of some parent. Yeah, then you have to make some further assumptions that are a bit uncontrolled. Yeah. He said he's going to ask a question that's going to make everyone hate him. Can you automate the solving of the cavity equations?
Yeah, like
Yeah, so this whole thing is entirely procedural.
And then there's some
Yeah.
answers.
Correct. Yeah. So if I also wanted people to hate me, what I'd say is that automation procedure is called students, but yeah, indeed, I mean it's a procedure you learn and then you can just deploy it on various things. The key is just figuring out what answers to use. Grad student descent, is that what you said? Sorry. Okay. Yeah. Okay. All right. Thanks everyone.